everyone, welcome back to my channel. In today's section, we are diving into a very important diagnostic tool in hematology, HbElectrophoresis. Have you ever wondered how doctors detect abnormal hemoglobin like hemoglobin S, hemoglobin C or thalassemia? Or how we can separate different types of hemoglobin based on their electrical charge and size? Well, that's exactly what HbElectrophoresis helps us to do. So, now let us discuss about normal structure of hemoglobin. Hemoglobin is made of 4 protein chains, 2 alpha and 2 beta. Each chain has a heme group with iron molecule. There are 4 heme groups bound to each chain. Each heme has an iron atom at its center that binds oxygen. See, there are 4 polypeptide chains, 2 alpha and 2 beta. Also, there are 4 heme groups. The iron in each heme can bind one oxygen molecule. So, the whole Hb molecule can carry how many molecules of oxygen? 4 molecules of oxygen. The chains are held together by hydrogen bonds, hydrophobic interactions and ionic bonds. It's very interesting, no? So, hemoglobin molecule is made of alpha 2, beta 2 and 4 heme groups. What's the function of hemoglobin? It transports oxygen from lungs to tissues and carbon dioxide from tissues to lungs. Actually, it's like 4 seats in a car. Each seat carries oxygen passengers. Then, see this structure. What happens if the seats in the car break? Will oxygen travel properly? Oxygen means the passenger can travel properly. Yes or no? Of course no. Okay, same like something happened here for the hemoglobin. Mutations change the shape of globin chains. Look here, these shapes are changed. Okay. For example, in HbS, RBC becomes crescent shape. It blocks blood flow. Same as in thalassemia, lesser or no production of certain chains. What will happen? Of course, the delivery of oxygen will become weak. This is the structure of a hemoglobin. The main types of normal hemoglobin are HbA, adult hemoglobin. Hemoglobin A or HbA1 is the major part of hemoglobin in a healthy adult. HbA2, which makes up a small percentage of adult hemoglobin, almost 3.5% or less than 3.5%, and then HbF, fetal hemoglobin, approximately 1%. HbF is replaced by HbA shortly after birth. Yes, everyone heard of adult hemoglobin, but have you met its cousin HbA2? Let us discover its role. What is HbA2? HbA has 2 alpha and 2 beta chains. But what about HbA2? Can anyone say? Instead of 2 alpha and 2 beta, in HbA2, 2 alpha and 2 delta. It has a big diagnostic role in beta thalassemia and other blood disorders. So now what we learned? I'll tell some tricks for easy remembering. HbA or HbA1, adult hemoglobin, is the main pilot. 98%. If we are telling in range 95 to 98% or more than 95%. It depends. Then HbA2, it's backup pilot. Less than 3.5% of adult hemoglobin, that fetal hemoglobin. That HbF, it's baby's uber, approximately 1%. Okay, now that we learn about normal structure of a hemoglobin, how do doctors actually catch the abnormal ones? Now it's our role. Let's play as a detective. Someone has anemia. Usually what doctors do? As usual, they may request CBC. Then we done the CBC report came and it gives some clues like low indices, MCV, MCH, like that. But it's not the exact diagnosis. We will get an idea of anemia. Then what we will do for next step? We will go to HbElectrophoresis. What happens when we put blood in an electric field? We will go to HbElectrophoresis to find out the underlying reasons for this anemia. What happens when we put blood in an electric field? Just imagine. Do they run together or they stay still or what? Okay, they run at different speeds. Even abnormal hemoglobin also take unique positions and doctors compare these bands and tells which type of hemoglobin is present. So as we discussed, HbElectrophoresis is a blood test that identifies and measures different types of hemoglobin. The test works by applying an electric current to a blood sample, separating hemoglobin types based on their electrical charge and size, making from visible bands. Why we are doing hemoglobin electrophoresis? Any idea? Why we are? We done CBC, we got the report, this HB and RBC indices are very low, we identified this as anemic. So why we are going for HB electrophoresis? Yes, there is some reasons. For identifying hemoglobin C diseases. In hemoglobin C disease, a mutation causes the production of hemoglobin C. It leads to mild anemia and other health problems. Next, screening for hemoglobinopathies. HB electrophoresis is used for newborn screening and in families with a history of hemoglobinopathies. It helps to identify people who may be carriers of hemoglobin disorders. One of the parents is carrier, it can transmit to children. Then for evaluating anemia, HB electrophoresis helps to evaluate the cause of anemia if the standard tests do not provide a definitive diagnosis. Yes, from iron profile and CBC examination, we can understand the patient is having anemia. But we need more investigation to find out what is the underlying reasons of this anemia or what kind of anemia it is. Then prenatal testing. If a family history of hemoglobinopathies exists, prenatal testing may be performed to assess the baby's risk of inheriting hemoglobin disorders. So this test can help to detect abnormal hemoglobin in early pregnancy. Diagnosing sickle cell disease. Yes, of course, sickle cell disease is the most well-known condition diagnosed with hemoglobin electrophoresis. In this condition, hemoglobin S replaces the normal one, HbA, leading to sickle-shaped cells that can block blood flow. Normal RBC shape, and this shape is becoming like a sickle. So what will happen? It blocks the normal blood flow and it causes severe pain, anemia and organ damage. Diagnosing thalassemia. Thalassemia is a group of inherited blood disorders. It's genetic disorder characterized by abnormal hemoglobin production. So HB electrophoresis helps to identify the types of hemoglobin produced and can diagnose condition like it's major or minor, or the patient is carrier or not. We can identify through HB electrophoresis. See, this is one of the instruments used for HB electrophoresis. As we discussed, HB electrophoresis test is a laboratory procedure that separates the different types of hemoglobin, normal and abnormal, in a blood sample based on their electrical charge and size. How the test is working? We can apply an electric field to a blood sample, causing the hemoglobin to move through a gel or liquid medium. Then different types of hemoglobin moves at different rates, allowing them to separate it and identify. Now we can discuss about the processes, how it's doing. Yes, of course, we need blood sample. For hemoglobin electrophoresis, we are using EDTA, anticoagulated venous blood sample. After taking the sample, we have to mix it properly void to preserve the hemoglobin and maintain its structure during the test. The prepared sample is then placed in a gel or liquid medium, and we can produce an electric current. We can apply an electric current. Hemoglobin molecules are charged particles and they move towards the electrode with the opposite charge. Hemoglobin with different electric charge and sizes move at different speed through the medium, separating into distinct bands. The various types of hemoglobin will separate based on their unique characteristics. Means depends on its weight, its charges, speed of moving. The separated bands, how we will identify? The separated bands are then analyzed and compared to known standards provided by the manufacturer. Usually we are using common medium like cellulose acetate with pH 8.4 and citrate agar with pH 6. You can see here this is normal pattern and abnormal pattern. You can compare this pattern also. Normal in cellulose acetate with pH 8.4, sample will flow from negative charge to positive charge. This is the normal pattern. This is the origin. We are applying sample here and it's moving towards positive side. This is A2, HbF and HbA. It's normal healthy adult, so HbA will be more than 95%. This is an abnormal pattern. I will discuss later these things. So now we can discuss about result interpretation. So firstly we can see a normal result. This is the hemoglobin normal pattern. We are applying sample at the origin. Sample is moving towards the opposite charge. HbA2 will be here and HbF and HbA like this. It is a normal pattern. The major type of hemoglobin in adults is HbA. It makes 95 to 98% of hemoglobin. HbA2, this is minor component of hemoglobin, approximately 2 to 3%, and HbF, this is fetal form of hemoglobin, usually found in small amounts, less than 1%. Sickle cell disease. Here you can see, easily you can identify HbS will be the more. This test reveals a high percentage of HbS and a reduced percentage of HbA. It confirms the diagnosis of sickle cell disease. Here also you can see sickle cell disease. This is common for all. So you can see here sickle cell disease. If the patient is with sickle cell disease, band will be here. Sickle cell trait, of course it's a carrier. Individuals with sickle cell trait usually have both HbA and HbS. HbA also will be there along with HbS. These individuals are carriers of sickle cell disease and can pass the gene to their children. Thalassemia. Thalassemia is a blood disorder. It's inherited, which means it passed from parents to children. You can see this table. In a normal healthy adult, HbF is like approximately 1% or less than 1%. Adult hemoglobin 95 to 98%. It's average 97%. HbA2 1 to 3% approximately. In case of thalassemia major, what will happen? In thalassemia major, HbA, adult hemoglobin will be absent and HbA2 will be variable. Then who will be there? HbF. In major thalassemia, HbF will be up to 98%. In thalassemia minor, HbF is variable and HbA2 5 to 10%. HbA is reduced 80 to 90%. HbC disease. Yeah, C disease. Then people with hemoglobin C disease will have HbC in their blood. See the band. This is the normal band. You can compare. In normal band, HbA2, HbF and HbA. HbA will be 95 to 98%. In abnormal, there is hemoglobin C. You can see a band here, hemoglobin C. It's typically associated with mild anemia. So in conclusion, sickle cell disease predominantly HbS with little or no HbA. Sickle cell trait, its carrier HbS present along with HbA. Thalassemia, elevated HbA2 or HbF. Hemoglobin C disease, presence of HbC. The test can also reveal other hemoglobin variants such as hemoglobin E, hemoglobin D or hemoglobin ORM, each with its own unique banding pattern or the electrophoresis. So manufacturer will provide a standard so we can compare the gel paper with that standard. This is an example. This is starting point, cathode minus plus. One thing I forgot to tell you, along with all the electrophoresis, we are running a control standard also. In case of normal adult, the pattern will be like this. The band will be like this, normal adult. If the patient is a normal newborn, it will be like this. In sickle cell disease, there will be one band in S position. Again, we are running on AFSC control. The sickle cell trait, it's a carrier. So, adult and sickle cell hemoglobin will be there. This is HbSC disease. HbSC disease, of course, S and C will be there. F for fetal and sickle also. Hemoglobin C disease, only C. These are for examples of cellulose acetate gel with pH 8.4 and citrate agar with pH 6. In cellulose acetate, pH 8.4, negative to positive, it's moving. It's normal pattern, it's an abnormal pattern. This is an example of citrate agar with pH 6. It's moving from positive to negative. Abnormal pattern is here. Here you can see two extra bands, Bart's and H. What is Bart's band and H? Yes, let us discuss. HB Bart's is an abnormal type of hemoglobin, mainly in newborns with alpha thalassemia. This leads to severe tissue hypoxia. Hypoxia means oxygen deficiency. Then HbH means 4 beta chains in place of 2 alpha to 2 beta 2. Normal case, in a normal healthy adult, 2 alpha and 2 beta. But in case of HbH, alpha 2 beta 2 is replaced with 4 beta chains. This leads to chronic hemolytic anemia. So in HB Bart's, 4 gamma chains and HbH 4 beta chains. It's commonly seen in newborns. This table reveals hemoglobinopathies under different conditions. See sickle cell anemia. Sickle cell anemia, what will happen? In sickle cell anemia, HbA1 is absent. Then who will be there? HbS will be there. 95 to 98% of HbS, 2% HbF, and HbA2 2 to 3%. Sickle cell trait, it's a carrier. So along with HbS, HbA1, adult hemoglobin also will be there. HbA2, HbF approximately 2.3% and 2% respectively. Beta thalassemia major, yes, in beta thalassemia major, of course HbA1 is absent, HbS, HbC, HbH, everything is absent. Then who will be there? HbA2 and HbF. In thalassemia, HbF and HbA2 will be there. HbA1 will be absent. Beta thalassemia minor, 50 to 85% HbA1 along with 4 to 8% of HbA2 and HbF. HbC disease, yes, of course, only HbC, 90 to 100% of HbC. So I hope that we understand the basics of HbElectrophoresis. To sum up, what is the normal pattern of hemoglobin, how the abnormal patterns will be, then how we are diagnosing this, and how will be the interpretation. If you found this video helpful, don't forget to like, share and subscribe. Thank you.